All right, hello everyone. Could one of you comment in the chat if you can hear me, just to double check? Cool. Okay. I'll wait another minute or so to get started, I guess, for everyone to get on. But how are you guys all doing? Okay, and I guess one more thing, if you guys who are here could comment, and basically I've had a number of students tell me that this time doesn't work for them. And so what I kind of tried to do with this time is it's kind of halfway between my other two recitation times, which were at 9:30 on Tuesday and 2:30 on Thursday. Obviously, because it's like that compromise, a lot of people, it's not going to work for them. So would you guys be free if I did it at Tuesday at 9:30, I guess? Would that work better for all of you? I guess, I don't know. I might send out an actual Google survey later, or if you can just comment in the chat, yes or no. But I'm thinking about moving it to Thursday at 9:30 or Tuesday at 9:30 again and go from there. But either way, we will get started. I'll start with my traditional joke as always. So H2O is water, H2O2 is hydrogen peroxide. What is H2O for? It's for drinking. So there you go. Great joke. Okay. So for now, basically today, all I'm basically going to cover is titrations. There are two types of titrations that you'll really have to worry about, and those are going to be a weak base titrated with a strong acid and a weak acid titrated with a strong base. And so basically I am only going to break down really the steps for doing a weak base with a strong acid. That's all these questions are kind of about. After that, I will do an example problem, or have us like all work through an example problem, one of each. But basically, I don't know, I just figured it would be kind of a waste of time to do both. However, so starting at this, as I kind of wrote up here, there are four types of pH calculations. This fourth one is the one that's after the equivalence point. You guys don't have to worry about that one, so I won't be doing one of those. I think in lecture today, Dr. Katz mentioned that your lab assignments might ask for that, but you don't have to worry about that, so I won't be working through any of those. If you're really curious, you're welcome to stay after Reci and ask me in my office hours, but otherwise, as I said, we're just going to kind of ignore that part and look into these other three. And so looking at that, kind of going into the steps for any titration problem, the first step, I guess, that I would always do is calculate the volume needed to reach the equivalence point. And the reason for that is it actually gives you a few pieces of information. First of all, what the equivalence point actually means is, I'm going to just write it out, the definition kind of here. So it's basically just going to be the amount of titrant added is enough to completely neutralize the solution. Sorry, it's taking me a sec to write on this, and the handwriting's really bad, so. Okay, so that is the definition kind of the equivalence point. One of the reasons why this is important is because in order to find what the equivalence point is, you're actually already determining how many moles of your compound you have to start with. And so since you're determining how many moles you have to start with, that'll actually help a lot with your later on calculations. The total volume at the equivalence point, just really quickly, is going to be initial volume plus volume of titrant added. And that will actually be really important when you get to the calculations of pH at that equivalence point, because you'll need to use that overall new volume. And I said why it's important to calculate this first. The main thing is it lets you know whether or not the calculation you need to make is one that you make at the equivalence point or before the equivalence point. So I'm just going to kind of say, just lets you know where you are relative to equivalence point. And so that's just kind of the first step then. Moving on, what I'm basically going to break down is, as I said, so these are just the steps for a weak base titrated with a strong acid. And so what I'm going to kind of do is just break down what's actually going on in solution at that time. We won't actually do any calculations for this. It's just a kind of the 3 types of calculations. And then we'll get into the 2 example problems, and I'll kind of give you guys a chance to work on your own. So initially, before any titrant is added, and for this we're doing a weak base with a strong acid, all that's currently in the solution is actually just that weak base. So I'm just going to write just weak base. And then how do you calculate the pH of a weak base? You should all be very familiar with that. This is where you're going to use just the classic ice table. So before you've added any titrant, it's just a solution with a weak base in it. All you have is an ice table. And once again, so you'll solve for the ice table, and you're going to end up using the equation that Kb equals concentration of OH minus times the concentration of Hb, or the protonated form, over concentration of B minus, which is just the concentration of what's left of the base. And so once again, to get this value, you're just going to use that classic ice table like you're used to as much as anything. This next part, so what must you calculate to determine the pH here? This is kind of a vague question, I guess, but you'll need to determine the Kb first. A lot of times it might only give you the Ka. You'll also need to determine the concentration of OH minus. So remember then, this will give you, when you solve for X, that gives you the concentration of OH minus. So you'll have to find the POH and then convert that to pH. So just kind of a series of steps there. Just a little bit of summary of what's actually happening at that point. So the second type then is actually after you've added some titrant. And so once you've added some titrant, you have to think about what you have in solution. And so basically what you've added, so we're titrating with a strong acid. So you have right now in solution weak base because of what's left over. You've also added some strong acid, and what the strong acid actually does is it converts weak base into its conjugate acid, and that's all it is. So all we're going to say is present in solution at this point is weak base and its conjugate acid. And I'll go over again later when we're actually doing the practice problems how you can do this. But basically, for every 1 mole of strong acid added, you're going to convert like 1 mole of base to 1 mole of its acid. And so then what type of system is this? This is where you get to something that we just ended with, which is a buffer system. So anytime you're here, you're basically going to do the exact same calculations you would have done with a buffer. If you think about it, it makes sense because all you have in the solution is that weak base and its conjugate acid. How do you determine the moles of weak base and moles of weak acid or conjugate acid? This is what I kind of actually wrote up here. But so, yeah, so every mole H3O plus added converts 1 mole of base to acid. So that's just kind of what you have to think about at these points. The last step then for pH calculations, this is where there's 2 methods of doing it. I personally do like the Henderson-Hasselbalch equation just because when you're doing these, Once you've converted these things to moles, which we've done here, you don't actually have to find the new volume at this point. You'll have to find a new volume at the equivalence point later on. But for now, you actually don't need the volume, because when you do the Henderson-Hasselbalch equation, I'm just going to write that as HHE. What you have then is that the pH equals pKa plus the log of moles of base over moles of acid, which I think is a pretty simple calculation. It is maybe a harder equation to memorize, but once you do have it memorized, you literally will just find the pKa by taking the negative log of the Ka. You can plug in these mole values, and then you get the pH. The alternative is that you can convert moles to concentrations. To do that, remember, you'll divide moles over the new volume. And then what you'll do is just plug it into this equation where you have Ka equals concentration of H3O plus times the concentration of the base over concentration of the acid, which is what you're used to. Another way of writing this would just be equals concentration of H3O plus times A minus over HA. And so those are the two ways of doing it. For any of these worksheet problems, you're welcome to do it this way, and you should get the same answer. I am going to work them out using the Henderson-Hasselbalch equation, though, just because that's what makes more sense to me, and I think it saves a step, at least at these points. So then moving on, the last type of equation you guys will have to be able to do with this is the pH at the equivalence point. And so remember, what I always do as my first step is figure out what volume that would be to reach the equivalence point. And so once you know what the equivalence point is, basically what that means is you've basically converted every single mole of weak base in this case. So every mole of weak base is now its conjugate acid. So all you actually have present in the solution now is just the conjugate acid. And so how many moles of the conjugate acid are present? If you think about what's happening, let's say you started with 1 mole of the base. You added enough HCl to turn all of this base into the conjugate acid. So now what you have would be basically 1 mole of the conjugate acid. So obviously it's not always going to be 1 mole. So you'll basically just have basically the same number of moles of the conjugate acid as the number of moles of the base you started with. So same number moles conjugate acid as the weak base you started with. Okay, so what is the total volume now? This, we already found the total volume at the equivalence point is just going to be initial volume plus volume added. And at this point then, to calculate the pH, so earlier for the initial when you hadn't added anything, basically, so all that was in here was just weak base. When it was just weak base, you used an ice table using the Kb value because you have the base that's dissociating. Now it's all the conjugate acid. So what you're going to use instead is you're going to use the value that you're going to basically use an ice table, but this time you're going to use the Ka version. So Ka equals H3O plus over concentration of A minus over HA. So once again, at the equivalence point, you've basically converted all of the moles of base into its conjugate acid here. You'll need to find the new concentration by dividing moles of conjugate acid over this new total volume. Once you've done that, the new pH is just going to be equal to whatever the negative log of this concentration of H3O plus is, which you'll find using this ice table. So are there any questions on that before we move on? Okay, and as I said, so this is just an example for weak base with conjugate acid. Everything here would be the exact opposite if you were using a weak acid with a strong base. So all you do for that one then is, if you think about it, at the beginning, you would just have weak acid. And then at this point, it is still a buffer system because you have some of the weak acid and some of its conjugate base. And then at this point, it would be all converted to its conjugate base. So it's the same type of calculation. It's just kind of inverse. And we'll do those with these review problems here. So I'll give you guys a second to solve 1A here. If you guys could actually, you can either private message me or public message me your answer when you get it, but just to kind of get an idea of when you guys are finishing up, because otherwise I'll really have no idea. That would be awesome, but I'll just give you guys a few minutes to try and work that out, at least until some of the answers come in. I'm going to pause the recording so people don't have to watch this. Okay, I'm starting to get some answers come in. And so you should have gotten 39 milliliters. So if you got that, awesome. I'll kind of just show how you would do that calculation right now. So the first thing you would do, and once again, I apologize if you're still working, no need to rush, but basically what you'll have is you have 45 milliliters of 1.3 molar ammonia solution. So the first thing I'm going to do is figure out how many moles of ammonia there are. To do that, I'm going to convert that into liters to start with. So you have 0.045 liters times 1.3 moles per liter. And that then is just going to equal 0.0585 moles. At this point, then you have to think about what the equivalence point is actually meaning. And the equivalence point will be when you've basically added as many moles of H3O plus as you have moles of this, so you can completely neutralize it. And so since HCl is a strong acid, for every 1 mole of HCl, I'll just write that up here, 1 mole HCl equals 1 mole of H3O plus. And so that means in order to figure out how many moles of H3O or HCl we need to add, it's just going to be the same thing as the same number of moles of this. So what I'm going to do is just divide 0.0585 moles divided by the concentration of HCl actually. So the concentration of HCl is 1.5 moles per liter. And what this ends up giving you is 0.039 liters, which equals 39 milliliters. That's kind of the calculation you'll need to do for this. So you basically will just make it so you figure out the number of moles of your weak base, and then you have to figure out how much volume of the weak acid you need to add to that, or strong acid, I mean. And to do that, you'll literally just divide moles by that concentration, and that gives you the total volume of the weak acid or strong acid you need to add. So once we reach 39 milliliters added, that means we'll be at the equivalence point. So this next question then asks for what is the pH before any of the HCl is added. And so looking back at the sheet for when a weak base is titrated with a strong acid, type 1 is before any titrant is added. So that's going to be this type of calculation. All that's present is just the weak base. And what we need to do is basically solve for this ice table, which needs the Kb, and then we'll find those concentrations. So the first thing we're actually going to need to do before we can really work out the ice table is I'm actually going to convert the Ka to the Kb. So it gave us the Ka of ammonium, but we need to find the Kb of ammonia, and ammonium is just the conjugate acid of ammonia. So what I'm going to do is do that Ka calculation. So remember, Ka equals Kw divided by Kb. And so to do that, we're just going to do 1.0 times 10 to the minus 14th divided by the Kb, which is, in this case, 5.8 times 10 to the minus 10th. And so that means you should get the KB to equal, let's see, 1.724 times 10 to the minus 5th. So now that you have the KB, I'll give you guys a chance to try and figure out what the pH is at this point. It shouldn't be too difficult because we've done a lot of problems like this, but it is kind of new. So once again, just let me know if you have any questions. I'm going to pause the recording again. And yeah, if when you solve it, if you could message me, just so I kind of know when at least some of you are finishing up, that would be cool. Okay, cool. I'm getting a couple correct answers in. So you should get a value of 11.67 as your pH. And so those of you who got that right, thank you. And so basically, I'll just work that out now. Once again, I'm sorry if you're still working. No need to rush. But what I'm going to do is basically just solve this ice table. So we have NH3 plus H2O goes to OH minus plus NH4 plus. We know the initial concentration of NH3 is just actually what it gave us as the concentration in the solution, which is 1.3 molar ammonia. So that means that we have 1.3 molar here. We can assume that these values are 0. So we'll do minus x plus x plus x, 1.3 minus x, x and x. Once again, water's a liquid, so you won't do that. Looking at what you have then, we have that KB, which is this value here. So we have 1.724 times 10 to the minus 5th equals x squared over 1.3 minus x. And what you're going to solve for here is then your solver ends up getting this equals 0.00509, which equals a concentration of OH minus. What you're going to get then is you solve for the POH, which when you take the negative log of this, you should get POH equals, I think it's like, what, 3.32. Subtract that from 14 to get the pH, and pH equals 11.68. You might have gotten slightly different, but that's just what my values gave me. As long as you're close to that, you probably did it right. So looking at the next calculation, so it asks, what is the pH after 15 milliliters of HCl has been added? The next thing I'm going to do is actually look back at what we figured out the volume to be at the equivalence point is. We figured that out to be 39 milliliters here. And so because 15 milliliters is before 39 milliliters, we know that we're going to be in the second type of calculation here. And that second type of calculation then is going to be pH after some titrant is added. And so at this point, what you have in solution is some of the weak base and its conjugate acid, and you have a buffer system is basically what you're going to be looking at. And so I'm actually going to kind of show how to do this first step of the calculation, just because I think it's a little more confusing, and then I'll let you guys finish from there. So the first thing I'm going to do is actually determine how many moles of HCl this is that we're adding. And so we're adding 15 milliliters, which is 0.015 liters. I'm just going to multiply that by the concentration of HCl that it gave us in our titrant, which it says is up here, 1.5 molar HCl. So this many liters times 1.5 moles per liter, which is just the definition of molarity. What this ends up giving us is 0.0225 moles of HCl. So this is how much HCl we're adding. What I'm going to do then, and there are a lot of ways of doing this, and this might not be the most, I don't know, the most official way of doing it, but this is just how I think about it, is we have in the solution now, as we add acid, we have NH3 going to NH4 plus. And so it is reacting, so it would probably be more accurate to throw in like the water and the OH minus values in here. However, I get a little confused when I look at that because it looks too much like an ice table. This is a little different than an ice table, and we're just kind of figuring out how the overall moles would have changed when they react completely with that strong acid. So what I'm going to call this is we're going to have our initial value here is going to be the initial number of moles, not concentration. Initial stress is what I'm going to call it, and nu. So there's no cool acronym with this one, but it's different than an ice table, which is why I use those letters. There are other ways you might see this written. This is just how I do it. But the initial here is going to be the initial number of moles of NH3 that were found. And we actually found that number of moles when we did the volume calculation here for the equivalence point. We figured out that there were 0.0585 moles of the ammonia in the solution. So we're going to use that as our initial number of moles of ammonia. So 0.0585 moles. NH4 plus, remember at the beginning when none of it's been converted yet, this is actually going to be 0 moles. So remember, initial is just what you started with before you added any titrant. What we're looking at now is how we stress it. And so what happens for every mole of HCl that you add, it's going to convert this into NH4 plus. So you can think about, remember, HCl is going to break up into H3O plus. So we're basically adding 0.0225 moles of H3O plus into the solution. What's going to happen is the strong acid here, for every mole of the strong acid, it's just going to add on to this and convert it into NH4 plus. So since there's this many moles of H3O plus, the stresses are going to subtract 0.0225 moles from this and add 0.0225 moles to this. And the new value, remember this isn't equilibrium or anything, so you can't call it equilibrium, but now how many moles are in the solution is this minus 0.0225 equals 0.036 moles. And then this 0 plus 0.0225 is just 0.0225 moles. And so that's what we actually have in the solution right now. So what I do, as I said, is I like to plug this into the Henderson-Hasselbalch equation at this point because you can just use moles. The alternative you could do is actually convert these into concentrations. And to do that, you have this many moles. The total volume you have now is actually 15 milliliters of HCl that we added, plus the original volume, which is 45 milliliters. So what you just have to do is divide this number of moles by 60 milliliters, or I guess 0.06 liters, and that would give you the concentrations. However, the Henderson-Hasselbalch equation allows you to keep this in moles, so I'm just going to do that. So we have that pH equals pKa plus log of moles of base, moles of base over moles of acid. And so I'll give you guys a chance to figure this out, just kind of a quick calculation to let you guys figure out how to use the Henderson-Hasselbalch equation, or you can use the other method, whichever is more comfortable to you. Remember, this is the pKa, not just the Ka, so you will have to change the Ka a little bit to do that. But yeah, I'll give you guys a few minutes to work it out from this point. And once again, I did kind of do a lot of the calculation here, but I'll let you finish it up and just make sure you're familiar with these calculations. Okay, perfect. So from the answers I'm getting in, people are getting it right. And so just to double check, if you use the Henderson-Hasselbalch equation, you have pH equals negative log of the Ka is what pKa means. So negative log of the Ka, in this case, the Ka was, 5.8 times 10 to the minus 10th. So 5.8 times 10 to the minus 10th plus log of moles of base is 0.036 we found here. don't know why my stylus is being weird right now. And then moles of the acid is 0.0225. Then all you have to do is plug that in, and it gives you the pH equals 9.44. And so there you go. The last type of calculation then is the pH at the equivalence point. And so for this one, I just specifically asked at the equivalence point. It could ask like, what is the pH at a certain volume? And you'll have to know that that's the equivalence point. Kind of depends on what the problem is actually asking. But for the pH at the equivalence point, we already figured out what volume needs to be added to get to the equivalence point. And we said that that is 39 milliliters here. And so we know what the new volume is going to be. We also actually then know what the number of moles of HCl is going to be too. Because remember, in this calculation, we made it so the number of moles of HCl equals the number of moles of ammonia. So 0.0585 moles will equal the number of moles of HCl, as well as the number of moles of the ammonia at the equivalence point at least. So I'm just going to write that this equals 39 milliliters added. And for this one, I'm going to give you guys a little more freedom to just kind of work through this and see if everything's making sense so far. Remember, at this point, you'll have to think what's actually present in the solution right now and figure out what type of calculation you're going to have to do. So I'll give you guys a little longer on this one just because, as I said, you'll have more work to do. Feel free to send me any questions that you have, or if you're having trouble getting started, I'd be happy to help. But yeah, I'll give you guys a few minutes to work that out now. Okay, keep working through it. I'm actually not going to talk as I work this out. I'm just going to kind of write out my work as I go, just so I can refer back to it later. But if you're stuck, you can kind of compare it to what I've done. Okay, and I'm going to kind of just explain what I've done so far before I start moving things. I have to zoom in a little bit to be able to write somewhat neatly, even though this isn't that neat, so I apologize. But basically at this point, what you have is you've added 39 milliliters of the HCl. As we said, we already determined that at the equivalence point, what that means is you're adding the same number of basically number of moles of HCl as you started with. So 0.0585 moles here. What that's going to give you then is when you subtract this, you'll get to 0 moles of NH3 are left, and all of those moles are basically converted into NH4 plus. So you have left in the solution is 0.0585 moles of NH4 plus. What that means is when you're looking at the concentrations, you now have the number of moles of NH4 plus. You have to figure out the volume. What the volume is this is the amount that we added, so 39 milliliters. This is the initial volume. So the total volume is just going to be the initial plus however much volume you added. This gives you that new concentration here. So this is now the concentration of NH4 plus. And remember, at the equivalence point, since everything is converted the other way, instead of a weak base, now what we have is just the weak conjugate acid. So you're going to want to do then is just do an ice table like we've done before. And so once again, apologize for the bad handwriting, but this is the ice table. Excuse me, you should have set up. So you have 0.0696 and then X and X. So solving for that, when it's a weak base again, you're going to actually use the Ka. So we have that the Ka, which let me look back to the problem. The Ka is 5.8 times 10 to the minus 10. So I'm going to zoom in a little bit. I apologize. I'll zoom back out at the end. But we have 5.8 times 10 to the minus 10th equals x squared over 0.696 minus x. We solve for that. Remember, when this value is really small, you could actually assume that this x value here is not there and just do x squared over 0.696. That's up to you, though. I still like to do this because it just helps me keep track of where I am. You get then that x equals, which is also the H3O plus concentration, 2.009 times 10 to the minus 5th. And that pH then is the negative log of that, which equals 4.70. And so this should be the answer you get for this problem. Notice that every time you're basically adding a little more of that strong acid. And so to start with, the pH was 11 point something. After we added a little bit, then it dropped to 9.44. Then at the equivalence point, it dropped to 4.7. So basically every time it makes sense, you're adding acid, you're decreasing the pH. And so there are only 5 minutes left in class. So you guys are free to go. Basically what I'm gonna do, as I said, I'm kind of just transitioning to my office hours at this point. There is a whole second problem here that's the other way around. So I will be here if you guys want to work that out and check your answers as you go. I will be here. You can just kind of message me or even turn on your mic and ask me at the end if you'd like. But I'll be waiting around. I don't want to keep you guys past the 50 minutes, I promise, though. So I will also post the answer key to this basically as soon as we're done here. I do have that out as well. But yeah, so if you guys would like to stick around, give this second problem a try. It's very similar steps to that last one. The only difference is I didn't guide you through quite as much because I don't ask for like, I don't know, I just asked for certain volumes added. So you'll have to kind of figure out where you are in the problem. And it's the other way around. So it's a weak acid with a strong base. But as I said, you guys are free to go and check this later if you'd like to, or I'll just be here. So I'm going to end the recording for now. And yeah, feel free to work it out. I'll be here answering any questions for the next 45 minutes or so. So thanks for stopping by. Also, guys, just let me know if you need me to slow down or move the screen up or anything if you want to see that. Okay, and that's the rest of the worksheet. So once again, I'll still be here for another 20 minutes or so, but feel free to ask any questions on this. I can move the sheet around if you want to see something from an earlier step, or if you have any questions on the homework or anything, just let me know. I'll be here. But yeah,